Welcome back, ladies and gentlemen. This should be the most difficult topic in the stoichiometry unit. Not necessarily the most complex, but it just has so many steps and it's so easy to get lost, especially because this limiting reactants builds on everything we've done up until this point, which means if you're not clear on the previous steps, this is going to get tricky. You're effectively, well, to use an analogy from physics class, you are effectively building a bridge across the river at the same time that you're walking across that bridge. If you're not very stable up until this point, you might end up falling in the river. Now, on the plus side, I'm here, and I will help you to get out of the water if that happens. So, let's start off by taking a look at limiting reactants. So it says here, up until now we've assumed that they have an unlimited amount of most reactants, which is reasonable in many cases. Right? So if I, for example, want to burn some paper, I can say there's an unlimited amount of oxygen in the air. Right? So for example, I can take the very page that we are using for our notes. If I wanted to burn this, I could just be like, light it on fire, and it burns. And what's going to run out first, the oxygen in the air or the paper that I'm holding? Well, this is one piece of paper. The air is, of course, a lot. It's a big room, plus there are vents that bring more air in, all sorts of stuff like that. So realistically, this will run out before the air does. Now, sometimes there is a limited amount of all reactants. Like, for example, if I tried to burn the paper while trapped in an airtight box. Now, I don't get infinite air, I get a limited amount. Usually one reactant will run out first. The question is just which one, and we call that one the limiting reactant or limiting reagent, and it means the same thing. Now, this name comes from the fact that the reactant will limit for how long the reaction can occur, or it will limit the amount of product that can be generated. Once you run out of the limiting reactant, everything stops. So the material that we have left over we call the excess reactant because it's unnecessary, it's extra. Now, this is all fine and dandy, but it's pretty nebulous, it's pretty abstract. We're going to go with something a little bit more concrete. Let's say you're trying to make a ham and cheese sandwich. You have 5 pieces of cheese, 6 pieces of bread, oop, I know what 6 is, and 12 extra digits, I got nothing, and 12 pieces of ham. How many sandwiches can you make, and will anything be left over? So we have, as written on the page here, a sandwich equation. Sandwich equation, of course, in this context is 2 pieces of bread plus 1 cheese plus 3 ham equals our sandwich. Specifically, 1 sandwich. Now, in this context, with the numbers that we have, right, how many can we make? All right, let's remind ourselves what the numbers are. So we're going to have, I think it said, what numbers did I choose? We said 12 pieces of ham. We said 5 pieces of cheese. And we said 10 pieces of bread, 6 pieces of bread. That's almost like 10. So what's going to run out first in this context? One of them will run out first, but which one? Well, one of the ways that we could try to solve this is that we could just simply work out how many sandwiches can we make with each of the different ingredients. So, for example, I have 6 bread. That is almost an A. There we go. 6 bread. I want to make 1 sandwich. Conversion matrix. See, look, I can use a conversion matrix for anything, including making sandwiches. Admittedly, these are chemistry sandwiches, so that makes sense, but anything. So I want to get rid of the bread, and I want to get the sandwiches. And the connection between the two is that for every 2 of these, you get 1 of those. So what do we get? We can get, not 1 sandwich, 3 sandwiches. Okay, that makes sense. I mean, obviously I didn't really need the conversion matrix, but there's a reason I'm doing this. You'll see in a second. Then we've got our cheese. Well, same thing. 5 of the cheese, brackets. We're going to do 1 cheese for every 1 sandwich. So we're going to get 5 sandwiches. Finally, the ham. We've got 12 ham, bracket. We're going to do 3 ham for every 1 sandwich. And that's going to give us a good old 4 sandwiches. Okay, so we figured out how many sandwiches we can make given each of these different reagents or starting reactants. But how many sandwiches do we actually make? Well, which one runs out first? The bread does. Once the bread runs out, I can't keep making sandwiches. I mean, I can keep putting ham and cheese together, but it's not a sandwich without the bread. Well, that's not totally true. Some people do those lattice wraps, and then there's at least one fast food restaurant that'll do like a sandwich that's just meat wrapped in other meat. Well, for our purposes, in order to make this chemistry sandwich, you need the bread, and we don't have it after we make 3. So that's it. We see that the bread here is the limiting reactant because it runs out first. In a lot of ways, what we've done here is we've sort of calculated some theoretical yields. These two are, of course, in excess. Which one is more in excess? Well, this one is more because, well, why because? Let's take a look. Meat and cheese are both in excess. Note, there is enough cheese for how many more sandwiches? Well, let's see. We had 5 pieces of cheese. We make 3 sandwiches, and then we have to stop. So how many pieces of cheese do we use up? Well, we used up 3. So 5 minus 3 is 2. So we have enough cheese left over for 2 more sandwiches, but we only have meat enough for 1 more sandwich. Why? Well, we started with 12, but we made 3 sandwiches. 3 times 3, right down here, is 9. 9 from 12, that's enough for 1 more sandwich. So we have enough for 1 more sandwich, but we have enough for 2 more sandwiches of the cheese. So that means that of these two, cheese is the most in excess, and the meat is close to being a limiting reagent of its own, right? If I brought more bread, somebody showed up and they said, here's more bread, Mr. C, I could only make 1 more sandwich before I ran out of meat. So that's the basic idea. And now we're going to take that basic idea and we're going to apply it to chemistry. Take a look at the next page. When trying to determine the limiting reactant, you first need to work out the balanced equation. And then remember, the limiting reactant is about which reactant runs out first. So the example we're going to work with here is we're going to burn 2 moles of propane and 7 moles of oxygen gas according to the reaction listed below. Let's get a little space on the board. But keep this in mind, because this and how we did this is going to be very important. So our balanced reaction is going to be with propane, which I think is that. No, not a P. Oh, Mr. C, it's propane, yes, but it's with a C. And then we've got, some oxygen gas is going to make some carbon dioxide plus some water. And it tells us that we're going to have 2 moles of propane and 7 moles of oxygen. So we're going to have 2 moles of this and 7 moles of that. And the question further then says, how many moles of carbon dioxide do we make? Okay, so I want to know that. Well, step 1 is always balance the chemical equation. We got 3 carbons here, so this is going to be a 3. 3 times 2 is 6. Oh, but we got another one there. But we've got 8 hydrogens. Let's get the hydrogens balanced. So we're going to put a 4. 4 times 2 is 8. So now in total for oxygens, we're going to have 6 here, and we're going to have 4 there. So that makes 10, so this is going to be a 5 in front. All right, good. Whew. I was worried it was going to be a hard one. says Mr. C, as people in the audience are going, ugh, balancing. It's been a while. All right, so there we go. We've got ourselves a balanced chemical equation. Now what do we do? Well, think about what we did with the sandwich. We then worked out how many sandwiches we could make with each of the different reagents, with each of the different reactants, right? With the bread, with the cheese, and with the meat. So let's do the same thing. We have 2 moles of propane. How many moles of carbon dioxide can we make with that? All right, let's give it a try. 2 moles of C3H8, and I want moles of CO2 equals. Okay, the balanced chemical equation is how we're going to do this with stoichiometry, and we're going to see that there's 1 of these for every 3 of those. So this is going to be times 3, that's going to be 6. So we have 6 moles when we're finished. All right, so we now know how many moles we could make of this product with this starting reaction. Now let's try the O2. With the O2, we've got 7 moles, so we've got more of O2, but we're trying to make moles of CO2 still. Oh, and I chose CO2 because the question asked for it. If the question asked for water, I could do that. If the question asked for nothing, I could choose whichever one I want. So down here, we're going to have moles of O2, and we know that one's a 5, and this one's a 3. So even though this is a much bigger number, this ratio is a lot steeper. So it might not work out so well. We get out our trusty calculator, we calculate it out, and we get 4.2 moles of CO2. So now remember what we did with the sandwich. The one that ran out first was what actually happens, because obviously I can't keep making more if I run out too early. So this must be the limiting reactant. This must be the excess reactant. So the question says, how many moles of carbon dioxide are formed? 4.2. That's it. We're done. All this requires is that we have the ability to compare 2 possibilities and choose the one that makes the most sense. When will the reaction stop? When one of these runs out. Which one is going to run out first? Whichever one makes less. Because that's how logic is, right? If I make less, I run out earlier. All right. That's for part A. There's a part B. Oh no, what are we going to do? Part B, what volume of carbon dioxide? Wait a second. Volume? That's just a conversion. I've got moles. I just need to turn it into volume. Well, that's not so bad. I mean, we've done that a lot. So I just take my volume. Let's do it with green. Sure. We're going to do like so. I want to get liters of CO2. So I put in 1 mole is equal to, let's see if you guys remember the number. I've written it. Can you guess what it was? Do you remember? I hope you do, because there it is, 22.414. Often people drop the 1/4 at the end, but whatever. I'm being particular today. You multiply that out, and you're going to get 94.14 liters. 94.14 liters. So there you go. How many moles did we make? This many. How many liters did we make? That many. This is very much like any other stoichiometry question. You're just bolting new pieces onto an existing framework. Previously, we started off with just doing this, mole to mole. That was stoichiometry level 1. Then we said, okay, good, you know level 1. Now I want you to do some conversions with it. So then we added conversions at the end and at the beginning. I could have given you these numbers not with moles, but with grams. Then you would have had to convert them. In this case, you didn't, because this is the first example. Let's not go too crazy here. But I could have made it so you had to do another step. But it's not a hard step. And really, the only part that we've added that's new is that we do 2 calculations, and we see which one runs out first. A theoretical yield, as it were. Okay, so that seems to be it. That doesn't seem so bad. Okay, there is one more step. Remember with the sandwiches, and I asked you how much cheese do we have left? How much meat do we have left? How did we do that? We took the amount that we started with, and we subtracted the amount we used to get what was left. We got to do that with chemistry too. Because, again, your boss might call you up and be like, hey, incredibly smart chemist that I pay lots of money. We can dream. Incredibly smart chemist, I pay lots of money. How much of that excess reactant you got left over? Can I sell it on the side, or maybe bring in another shipment of the original limiting reagents so we can do this again? You got to be able to tell them. Not to mention, it tells you how much you got to store away for later. So if you flip over the page, it talks about this a bit. Sometimes the question will go a bit further and ask how much excess reactant remains after the reaction was finished. This is like the sandwich example, asking about how much cheese was left. This way we do this involves subtraction. So it says here, excess reactant initially minus excess reactant used equals the amount that's left. In the case of the sandwich, we started with 5 cheese. We used 3 cheese, so we had 2 cheese left. Now, in the case of propane, a little bit more work. Okay, so when we're working with everything, of course, remember we work with moles. So the blue stuff over here. This was necessary to answer part B of this question, but right now, I don't really need it, so I'm going to get rid of it to clear up some board space. But now we're looking at part C. How many grams of excess reactant remain? Ooh, we got a gram request in there, but we're looking for excess reactant that is left. Now remember what it said. Initial minus used. So we have to figure out how much was used. Well, we know that this is how much product we made. How much propane do I need to make this much product? We already know how much oxygen we need. We need 7 moles of oxygen. But how much propane do we need? We can solve that. That's not so bad, really. It's just a normal stoichiometry question, but in reverse. The reason why limiting reactants are hard is just because there are so many steps. It's like I've put 6 or 7 limiting reactant questions into one, as opposed to just a single question. If you keep track of it all, though, it shouldn't be too bad. So we are starting with 4.2 moles of CO2. And I want to know how many moles of C3H8 do I need to use to make that? So this is just stoichiometry going from here to there. Now, how do we get this original 4.2? We got it by figuring out which of these two over here was the limiting reactant and then converting it. And then now that we've gotten here, we're going somewhere else with it. But in terms of what we actually do, it's just a simple stoich question. Nothing fancy about it. So we've got down here that the carbon dioxide is 3 and the propane is 1. So all I have to do is take 4.2 and divide it by 3. So when I do that, I end up getting 1.4. Now, this 1.4 is the 1.4 that I used in order to make this 4.2 moles of product. What I'm saying is, of course, that we ended up using up this much. Now the question is, how much did I start with? I started with 2. So I can write that out, and I can say that I started with 2 moles of propane to start, and I want to subtract the 1.4 moles of propane used, and that should give me the moles of propane left. And that's it. That's all we really needed to do. The reason why limiting reactants are so difficult has almost nothing to do with the actual individual steps. Yeah, there's a lot of steps. I mean, let's think about this, right? We had to do a balanced reaction. Okay, so that's one thing. Then we had to do potentially conversions, right? In this example, I didn't give you the starting reactants in grams. I gave them to you in moles. But if I did give them to you in grams, that would have been 2 more conversions. So there's 2 more. We're at 3 things already. Then you had to do stoichiometry twice with sort of 2 theoretical yield calculations. That's 2 more. We're up to 5. Then you had to figure out which one was the limiting reactant. So there it is. Then, sorry, there it is, limiting reactant. Then you had to convert it into the final answer. In this case, it was to volume, so that's 6. That's 6 steps already. Well, that's just 6 steps to get the answer to the first A and B of this question. We have to keep going, though, because then it says, what's the excess? Well, that's another question. Step 7, here's another conversion. Then I have to do a step 8, which is just to work out this. It's not a stoichiometry question. It's not a conversion matrix question. It's just subtraction, but we still got to do it. So we're up to 8. And then I'm still not done even when I get that final number there, because it's going to ask us in grams. So I have to do one more conversion. That's 9 steps. This question has a lot of stuff going on. There are many, many, many different steps. And that's the reason why people have a hard time. First of all, it builds on everything we've learned before. So if you're a little unclear on some parts of this unit, you get to this, you're just like, what's going on? There's everything. The other part of this is that while you're trying to do all of this, it's super easy to get lost. Where are these numbers from? What do they mean? But to our advantage, all of this is stuff we've done before. Yes, there's a lot of it, but we know it, right? Conversions are not a big surprise. Neither is balancing a chemical reaction. I really hope subtraction isn't a surprise here. It's just about figuring out the right numbers. So that's why we want to keep organized. All right. Enough distraction. Here we go. We take our 2, we subtract the 1.4, and we're going to get 0.6. So there we go. 0.6 moles of this propane are left. So now we know how much. Now we can store it. Now we can order more and use up the other stuff. Whatever we need to do. The final step of this question, of course, is a conversion. In order to get a conversion going, we're going to need to take that final last piece, 0.6 moles of C3H8 brackets equals, and we're looking for grams of C3H8. Admittedly, we'd often list propane as a gas, but whatever, we're doing it in grams this time. We're going to be getting moles on the bottom and grams on the top. Now we're looking at C3H8, so we're going to do, let's see, 12.01 times 3 plus 8.08. We're going to get 44.11. That times 0.6, we get 26.47 grams. We're finally done. I know, it took forever, and at least one shirt change. Turns out that a limiting reactant question can have a lot of steps. There's a lot of parts, but on the plus side, there's nothing you haven't seen already. This is going to take practice. It's probably going to take an awful lot of practice. So to that effect, we have got a bunch of practice. On the very next page, you guys will see there's another example for you to try, talking about some phosphorus and, where's the word, tetraphosphorus decoxide. After that, there's even more questions. Now, this very next example in the very next page, that one is in your book, in the answer book, so you can check there. The other questions have answers in your booklet, so it should be even easier for you guys to do it. So there you go. This is limiting reactants. And at the end of the day, it's not actually all that different. Really, the only 2 things that were new was that we had to do a theoretical yield calculation on both of these, right? We did 2 possibles and said, which one of these is going to actually happen? The limiting reaction one. So this one here doesn't exist. Didn't really happen. It could have, but it didn't. This is what happened. That was one step that was new. We had to do this twice. That's not so hard, doing 2 questions. We can do 2 questions. The other big thing was figuring out how much was left, and that was just subtraction. How much did I start with? How much did I use? How much is left? That, by itself, isn't hard, right? If we saw it with the sandwich question, if I ask you to do that with the just sandwich with cheese in the sandwich, it was very easy, right? You started with 5, I used 3, I have 2 left. Here it's harder because in order to get the numbers, you have to do stoichiometry. So it's an extra step, and it's an extra step that we're not necessarily super comfortable with yet. But you will be, because you guys are chemists in training, and soon, you will just be chemists. Training no longer required. Okay, guys, I'm going to leave it there, and I will see you next time.